All right, so today we're going to look at transformations. This is something that hopefully you did at least some of um, in your, I don't know, 7th or 8th grade class. We don't need to know a whole lot about these. We're going to use these primarily so that we can talk about things, but not so much as something that I'm going to test over heavily at all. Okay? So a transformation is just a change in the position, size, or shape of an object. The original figure is called the pre-image. The new figure is called the image. I've always disliked that, actually. I've always thought that the original should be called the image and the one afterwards should be called the post-image. That would make sense. But this is the way that it's done. So the original is called the pre-image, the new is called the image. A transformation maps the pre-image to the image. So here, what they're telling you is that triangle RST gets mapped to triangle R, and that little thing that looks like sort of like a single quotation mark, it's not actually curved. It is straight, and that's on purpose. That's read R prime, S prime, T prime. It just tells you how to match things up. Almost always they just use the same letters and add a prime just because that makes it easy. But you could have one where triangle ABC maps onto triangle RST or something like that. And this tells you how to map them. The first letter goes with the first letter, the second with the second, and the third with the third. It just tells you what goes where. So this tells you that we're making a transformation. So this would be like transforms to R prime, S prime, T prime. Now, there are 3 congruence transformations. In these transformations, after the transformation, the new shape is still congruent to the original shape. The first one is a reflection. You may have, in earlier classes, called it a flip. That's not the mathematically correct term. It does, explain it, but we'll use a reflection. So a reflection is a transformation across a line called the line of reflection. Each point and its image are the same distance from the line of reflection. So if we were to measure from A to the line, and then from the line to A prime, these two would be exactly the same length. So the point on the line of reflection is going to be the midpoint of those two. One thing to notice is that these are always measured along a segment that is perpendicular to the line. Students will often say, well, if I'm measuring the distance from point B to the line, I need to go straight to the line. And that's close, but not quite right, because if I go from here to here, am I going straight to the line? Yes, that's very much straight. What they actually mean when they say straight to the line, they mean perpendicular to the line. So the distance from a point to a line is always measured on something that is perpendicular to the line, not like this. So I could do the same with B and B prime and C prime. Each one of those would be equidistant from the line of reflection. So it's a little bit like, if you were to draw this with very wet ink or something and then crease your page here so that you folded it over, you opened it back up, this is what that would look like. A rotation, or what you may have called a turn in, again, elementary classes and the like, is a transformation about a point called the center of rotation. Every point of the image is the same distance from the center of rotation as the matching pre-image point. So here, for example, the distance from R to P is the same as the distance from R prime to P. And it doesn't quite look like it in my diagram, but you'll forgive me, please. So this distance and this distance are the same. So what's happening with a rotation is that point P is the only point that remains motionless. And then if you think about, you can actually take your paper. If you held point P still and took your paper and turned it, that's what's going on here. So QRS, and I guess I should put the triangle symbol on both of those. Triangle QRS maps onto or translates to Q prime, R prime, S prime. Notice when you do this, when you turn it like this, the triangle is going to be exactly the same size and shape as it was originally. That's why this is one of the congruence transformations. And the final one is a translation. A translation, or again, what you may have called a slide in earlier math classes, is a transformation in which all the points of a figure move the same direction, the same distance. So what does that mean? Well, that means that the distance from, sorry, let me try that again, from M to M prime and from L to L prime, those are going to be congruent to one another, and here's a new symbol for you, they're going to be parallel to one another. And the same would be true for the distance from N to N prime. All three of those segments are going to be congruent and parallel to one another. Yes, ma'am?
Before the LMN, is that a delta or a triangle?
It's a triangle.
How do you know the difference?
That's a great question. The answer is, in geometry, we almost never use, I don't think we ever use delta anything.
Besides delta x and delta y?
Well, and we actually, most of the time, don't bother calling it delta x and delta y in geometry because we don't do a lot of slope stuff. But yes, other than that. Part of it is that it has three letters. So with, when you're using delta, it's almost always a single letter because it's some variable. It's a great question. So, a question for you. How could you translate an angle in a way that would give you vertical angles? How could you translate an angle? Would you do, I'm sorry, and I apologize, I used the wrong word here. Let's fix that. What type of transformation? Yes, sir.
Reflection.
Okay, a reflection, as long as you reflect it over
The y-axis. No,
Well, it would depend on where the angle is.
Yeah, as long as you reflect it over the axis of the point as well.
That the what? I'm sorry.
The point in the middle of the angle.
Yeah, help him out. What's that called? Anybody? Someone said the right one. No, there's no midpoint in an angle. The vertex. Yeah, it's got to be. You got to be reflecting over a line that goes through the vertex. The other part of it is that the line of reflection needs to be perpendicular to the angle bisector. Don't write anything for just a second. Just watch. If I started off with this angle, oh, that was interesting. So if that's my angle, right? And then my line of reflection was like this. Is that going to end up with vertical angles? Mm-mm. And the reason why is because if I was to draw in the angle bisector here, is the line of reflection perpendicular to that angle bisector? No. So you can do it with a reflection. Bless you. Oh. But you have to be careful about it. So a reflection over a line that contains the vertex of the angle and is perpendicular, and that's the symbol for perpendicular, to the angle's bisector. It would have to be all of those things.
Could you show us an example of that?
Yeah. All right. So let me erase this one over here. Why are you not erasing? It's making me erase them one at a time. That's annoying. All right, so let's say I start off with an angle. And I'm going to freehand this because then I don't have to do all the other stuff. So let's say that's my angle, right? The angle bisector, I'm going to draw it with a dotted line, would be about there, right? So my axis, or my line of reflection, would need to be about like that so that it's at a right angle.
So it like makes an X? Like a perfect X?
Yeah. If you do it this way, then this is going to go this way, and this is going to go this way, and now I've got vertical angles.
Oh,
Okay? There's a simpler way to do it than this, though. What would be a simpler... Yes? I'm sorry? How much? Yes? Around what point? Pardon? No. Because if you had this and you had your angle over here, if I rotated 180 degrees, I'm sorry? A point, well, so if I rotated it around this point, would that work? You've got the right idea. It needs to be rotated 180 degrees, but hang on. But we need to rotate it around a specific point. Yeah. What point do we need to rotate it around? Got to rotate it around the vertex. 180-degree rotation. Around the vertex. That would also get you a pair of vertical angles. All right, let's go on to page 3. Hopefully you can kind of see the grid on this. So it's pretty light, but I think you can do okay with it. So a figure has vertices and it gives you these 4 vertices. So let's draw this. So point E is at 2, 0. F is at 2, -1. So my E is right in the way. G is at 5, -1. And H is at 5, 0. Okay. So E, F, G, and H. So those are my original vertices. After the transformation, the image has vertices. E prime is at 0, 2. I'm going to do this in a different color because I can. So 0, 2. F is at 1, 2. G prime is at, 0, 2, 1, 2. G prime is at 1, 5. And H prime is at 0, 5. So E prime is here, F prime is here, G prime, and H prime. So, what sort of a transformation is that?
Rotation.
Yeah, it's a rotation. And if we wanted to give more information about it, what are we rotating everything about?
0, 0.
Yeah. What's the name of 0, 0?
Origin.
Yeah. So it's about the origin, or you could say 0, 0, that's fine. How far did we rotate it?
90 degrees.
And which direction?
So then
Did we rotate it clockwise or counterclockwise?
counterclockwise.
Counterclockwise. All right. One more problem. Find the coordinates for the image of triangle JKL after this translation that says xy translates to x minus 4 and y plus 3. So, for example, point L has coordinates 3, 1, right? So that's going to map onto 3 minus 4 and 1 plus 3, which is to say it maps onto negative 1, 4. So that's where L prime is going to be. So then K is at 6, negative 1. So 6, negative 1 is going to map onto 6 minus 4, negative 1 plus 3. So that's going to be 2, 2. And then J, which is at 2, negative 3, maps onto, that'll be 2 minus 4 and negative 3 plus 3. That's going to map onto negative 2, 0. And that'll be J prime. Now, if you don't want to take the time to write this out, that's fine, because basically what this says is the x's go 4 to the left and the y's go up 3. You can just count that if you're graphing it. If you want to do this, absolutely fine, but it's not a requirement. Okay, any questions? Yes, ma'am.
Wasn't it at some point with the x-axis when you're subtracting it goes to the right and when you're adding it goes to the left?
That's when you're doing transformations of functions, but that's not what this is. So if you're doing, for example, if you're graphing the square root of x, and then you graph the square root of x minus 2, that's going to move the graph to the right 2 spaces. Is that what you're thinking about?
Yes.
Okay, yeah. All right. Your assignment is